Yeah, so we are we're going to do pre-training and fine-tuning of models. But because I want to squeeze in as much as possible, I'm going to do a bit of pre-training and then a bit of fine-tuning. So for pre-training, well, we're not going to do a big model, right? We could have done pre-training with a more complex game, for example, chess or something, right? But I just want to use this little tic-tac-toe transformer model, right, to demonstrate pre-training. And then after that, we will now go into fine-tuning. Pre-training normally takes a lot more, right? Um, so interestingly, there is actually a cargo data set that was generated by a group of folks who wanted to um, you know, generate a data set for training tic-tac-toe um, models. I've actually seen here that they have a bunch of models that, let me show you. Um, okay, so there's a tic-tac-toe data set. But for me, I think for me, the more interesting stuff is really on, um, training it to learn by itself. That's called learning by self-play, but you could actually train it on data like this. This is kind of um, training it on a data set. So if you can look at this data set, you have the columns are move one, move two, move three, move four, right? And then the actual data is a number that represents which square you should play, right? So and then you have a bunch of additional. So you have the data set contains a sequence. So this is something you can actually use to train a sequence model because it contains a sequence. And after you have trained on that sequence, right, the classification is whether it's a win or a loss. So in this case, you could use this to train a sequence model and the basically okay, first move is move zero. So zero is at the top right. Depends on what um they have used. There's actually GitHub here and Play Store where you can look at um how they implemented the interface. So probably zero means the top right, top left, and 8 means bottom right. So um in terms of the regular tic-tac-toe um layout. So you would have a layout like this. So something like that, which is a 3 by 3. And then if you had a 3 by 3, that means here would be zero. That's just that's how I would encode it, right? Here would be zero, and here would be 9. Sorry, here would be 8. Since it's 0 to 8. So it goes from left to right. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8. So if the first move one is 0, that means I'm placing it here. All right. And the second move two is 8, which means we place it here. And move two is the second um player, right? Then move three will be back to the first player. and a place in was one, which is this place. So with this, you have kind of generated a sequence of moves, right? First one, two, three, first three moves, the first four moves, and then maybe you can learn the rest of it, right? Or you could then you also give it the final you know. So if I played 0, 8, 1, and then 3, right? Um, then you know it's a loss for the last person, but it's a win. Because no matter what this person plays, okay, 3 is the second, then this is a loss. So 0, 8, 1, 3, then of course the next move is a 2, and it's a win. So anyway, but if I were to train a model, I would not use numbers like this. Numbers like this would work for tic-tac-toe because it's a simple game. But when you're dealing with more complex games, it's better you use a probability distribution. So in the context of a transformer, what you would give the transformer is a sequence that contains maybe the history, or even like in the case of transformer, you don't even need to give a history. You just give it numbers that represent positions, right? You do a kind of encoding that represents positions. And then based on that, you also give a distribution that represents the next move that should be made. So that's kind of standard representation, in most of these games like chess, checkers, and so on. So the way I would have encoded this would be I would unroll these 9 positions, right, into a sequence, right? And those are the inputs that I'll send in. And so for each of those positions, I would encode who has what piece has been placed there. And we can have two values, or rather 3 values. So you could have 3 values. One value would mean nothing has been placed there. Another value, maybe like 0 could mean there's nothing placed there. 1 could mean white or X, and 2 or -1 could mean um, you know, Y. That is black or zero or zeros, right? That is not. So that could be a representation. But anyway, let me just try out because I have a bit of the code already. Let me see how I can place that here and we see what comes from it. So okay. So the first step is representation, mod representation, the data representation. And then the second step is your, uh, machine learning model that you would use. So let's start first of all with the, okay, so let's start with representation. So representation, we have a board, right? So you have to have a way to represent the board. And to represent the board, um, we create this, well, I'll start by importing NumPy. So we create this class, and you can see that if you look at this empty, so like I said, I represent an empty board with 0, and then I represent X with 1, that means player 1, and I represent O with -1, that is player 2. So it's always good to do something like that because that really makes it very clear. You create a clear difference. This is a tri-state kind of situation, right? Where you need to clearly represents the three states of each square on the board. So, and that's just it. Zero for nothing on the board, one and -1. So you see the clear difference. It's easier when they're far apart that way because the model, that's different. Remember what we talked about linear separable, and all of that. So the difference is far apart enough that your model can actually easily predict. Okay, then there are things we also need to keep track of. This is just for the purpose of classification because what you want to do is you want to classify um, two things. Whether it is there are two ways you can do it. You can do what we call a policy distribution. A policy distribution is kind of a distribution of think of it like a distribution of numbers that says what is the best move to make? What should be the next best move to make when I'm in this particular situation, right? So that's a policy. While the value is like saying, is this current position a winning position or a losing position or a drawn position? So in order to be able to do that, we first of all create this list that contains winning situations. So winning situations in tic-tac-toe is you line it up on the row. So again, remember, we're talking about um, 0 to 8, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, right? That is a structure. In fact, let me put that in here so that it's easy to see the actual board, right? The board is going to be in this shape, right? Where you have 0 for this position, 1, 2. Then you have 3, 4, 5. And then you have 6, 7, 8. So just think about a simple tic-tac-toe. So this is how we number the positions. Now, the interesting thing is that when we're doing CIFAR 10, right, there's something we call data augmentation where you can rotate. And when we're talking about CNNs, we're talking about space invariant, meaning if you move things around or if you rotate, it doesn't change anything. The truth of the matter is that we can use this as a normalized board position and we can always rotate any position. And in this situation, it should be position invariant, it should be rotation invariant, it should be translation invariant. The rules remain the same for tic-tac-toe, irrespective of the position of the board. Even if I rotate this board 90 degrees, right? And if I were to rotate 90 degrees, this is what will happen. You would now have this is a 90-degree, let's say 90-degree clockwise rotation. So I rotate it something like this. If I rotate this board something like this, right? That's a 90-degree anti-clockwise, counterclockwise rotation. Then what we will get will be the 0, of course, comes down. So you will have the 0 this way. The rows become columns, right? You have the 1 up here, then you have 2. So that's the rotation. And then you now have 3 this way, and then you have 4 here, and then you have 5, and then you have 6, and you have 7, and you have 8. This is rotation. So in this case now, we now have this row 036. This column 036 becomes a row, right? While this column 147 also becomes a row. And this column 258 also becomes a row. And it's interesting that that is also, represented here. So we actually have the 0, 1, 2, which is the rows, 3, 4, 5, 6, 7, 8, as the lines. Basically, if you line up 3 in any of these positions uh, of the same type, then that's a win, but also in columns. So columns are not actually transpose per se, but you could view them as transpose. This is a rotation, but this is a transpose, just to let you know the difference. if I were to transpose this, right, then this column will become the row. So it becomes 0, 3, 6. So the main difference between a rotation and a transpose is that the columns still come. So in a transpose, it's a flip. It's a flip along the diagonal. That's a transpose. So think of a transpose like I flipped it along this diagonal. So I have this diagonal, and then everything that is on this side of the diagonal, I flip it around. That's actually a transpose. So it is not a lateral rotation, but it is an axial rotation, if you can call it that. That's what a transpose is. So if I were to do that transpose, you will now you see that this 036 becomes 036 here. This 147 still becomes 147 here. And then this 258 here becomes 258 at the bottom. So the main difference is just now they are still in the same order. The only difference is that here this one is at the bottom, but this one is now at the top. So you can think of a diagonal flip as being, or a rotation, right? A rotation can be seen as a diagonal flip. This is a rotation, while this is a diagonal flip. So you can see a rotation as a diagonal flip followed by a vertical flip. So if I did flip and then I flipped, this way, in other words, I now have this axis, right? And then I flipped around this axis. This will now become the same as this. So, all right. So anyway, those are things to think about when you are making games and all of that. The fact that they are rotations, transformations, translations, basically things you can do that you think that they are actually different, but they're not the same. But from your own human standpoint, you can see that they're actually the same, right? So anyway, this also includes diagonals because in tic-tac-toe, a diagonal position, a diagonal lineup is also winning. So this is just telling us these are the different positions. So let me also, this is rotate 90 degrees clockwise while this is transpose. So anyway, it's just for the sake of you know. Okay, so so this is the board. So the board is basically a list of 9 numbers, and we start off with empty numbers, so 9 times, right? Then the current player is X, so we are just using the letter X, which represents 1. It stores the value 1. So to make a copy of the board, yeah, you just basically copy cells and set the current player. Legal moves are to check the cells. Basically, legal moves are only cells that are empty. So you enumerate all the cells and you come up with the one that is empty. Then for you to make a move in any particular position, if the position is given, which of course it will given, you check if the cell is empty. If it is not empty, then it is an illegal move because you cannot place on a cell that is not occupied. And if that is okay and it's empty, you just replace whatever is in that cell, which is empty in this case, with the current player's value, right? And the current player's value should be either 1 or -1. So if the current player, and that's why it started with current player being X, that is what is in X. And remember, what is in X is 1. So if the current player is 1, then that means you place 1 in that place. And if the current player is -1, that is the person that has a not, then you place -1 in that current player. Then after making the move, you will switch player by just applying the negative sign. So remember, the X player is 1 and the O player is -1. So if X player is the current player, after he has made the move or he or she has made the move, then the next player should be the O player who is -1. So make move will place the the correct mark and also switch to the next player. So winner is to detect if somebody has won, right? So it checks through all of these 9 different or 8 different winning conditions, and if any of them is true, then there's a winner, right? So that's basically what this logic does, and I think we all did something like that. So what we just do is to do a sum. In this case, a short way of doing it is to find a sum. If the sum is 0, that means there is no winner. It means nobody, because 0 means 0, 0, 0 in the 3 lined up positions, or 1 minus 1, 0, which means a player and the opposite player. That's what 0 is. Um, so if it is 0, the only winning situation is if all 3 are ones, in which case S is 3, the sum is 3. And then in which case, it's the X person that won. But if all 3 are, if the sum is -3, that means all 3 are -1s. So we know that it's O that is the winner. Otherwise, return empty, meaning nobody. If it's terminal is to check if the game has ended, right? So self.winner, to check if the winner is not empty, that means somebody else won. So it's terminal, game has ended. But if not self.legal move, so legal moves is a calculation of how many legal moves are left, right? Which is this. So if the number of legal moves left is 0, that means no more legal moves. So it's also terminal, it's a draw. Result. So again, final outcome from X perspective. So this is a result from X perspective. If it is 1, that means X won. If it's -1, that means X lost. And if it is 0, that means it's draw. It's basically the same as the numbers you put in here for X. So just pulling the winner value gives you the result. So now all of this, right? In order for us to train a model with this, we have to convert this to tensors. So to make it into a tensor, we actually have to turn it into a tensor shape. So we bring in the torch and um, the encode. This is the encoding, right? Which is basically a list for now. Then you now check all the cells. So if the cell is an X, right? You encode this. So in encoding into touch, we now use a one hot, right? We don't just use numbers because you don't, gaming is not a regression problem. Gaming is a classification problem. I want to select which move to make. So you should not use actual numbers. That's what this is, right? I cannot say, let me just encode the number 0 as a position that I should play or the move I want to make. Okay, I want to put it in position 0. So the move should be 0. No. If you turn gaming into a regression problem, you have a very bad model that will not perform well. The best models in gaming are, everything has to be a classification. In other words, you have to use a one hot to encode the input, and you have to use a probability distribution to encode the output, right, that you want to train on. So in this case, we want to encode the input, and we have 3 different numbers to represent. So we have a 1 and a 0 and a 0. This is basically a one hot encoding, where the first position means X, right, is the one that is in that position. While the second position in the a one hot encoding means there is nothing there. And then the third position in the encoding means O, right? What corresponds to -1. And the reason why you see that the X is so far is on the other side, we put 0. 0 means there's nothing in that cell, right? And we're putting in the middle of the one hot encoding. Is to separate the two positives. We could have also made, if X, okay, sorry. Oh, I think I made a mistake. Yes, I was saying we use the third one, but we're actually using the second one to encode the not, right? This is not 0. This is -1. This is the not player. That is the O player. So that's the second person in the not in the one hot encoding. And then the third one hot encoding means there is nothing there, right? So you turn this into a tensor. The tensor is going to give you 9 by 3. right? That will be the dimension, 9 by 3. 9 is each cell, the number of cells, and then 3 is the one hot encoding that we are using. And this is it, all right? Is X is the first slot in the one hot encoding, is O is the second slot, and is empty is the third slot. So this encodes it into that tensor thing. Then this is just a string representation of the board. So this is a board class, and the board class just handles all of that. So after you have defined your board, then the next thing you want to do is, um, define the with the model is we'll go ahead with the model, right? Um, so we start by creating players. Okay, so we have the player is given the ability to make moves and so on. So you have multiple players here. You have a random player that is created. So a random player is a player that basically just chooses moves randomly, right? By looking at all the list of legal moves and picking one. And again, remember, a move is just an index, which represents where on the board you want to place. So that's a random player. Then we have this class for a model player, basically a player that is based on the trained model. So you can choose when you are creating the player to add temperature. Temperature allows it to do more random stuff outside of what you trained it to do. So the model is actually the model you have trained, right? So you specify that. So if you want to choose a move, then you first of all take all the legal moves, right? Then you take the board, you convert it to a tensor like we have seen here, which is a one hot encoding of the 9 positions that also contains what is in what is in the board at that time. Unsqueeze the first dimension, right? So that means unsqueeze means add an extra dimension. Squeeze means reduce dimension by 1. Unsqueeze means you add an extra dimension. So you see, we now add an extra dimension, 193. So we now have the first dimension, which represents a batch. Okay. Then we have 9, which is the number of um, squares on the board. So think of that as the sequence length, right? Because we're using transformer now. So think of that as the sequence length. And then 3 is the one hot encoding of what is in each uh, position in the board. So think of this as the encoding or the embedding. That's basically what it is. Because an embedding is just a kind of encoding. It's not a one hot encoding per se, but it's an encoding, right? So it's an encoding that represents a meaning. So in this case, this is what we have. So to now get the logits, you now take this position that we have created. So I will show you of course, we'll create a model that is able to interpret this and you train it on it. But you pass this into the model will give you the logits. And the logits, again, is 9 positions, right? The 9 positions basically is saying which of this is a probability distribution. So you have to squeeze again. Squeeze means you reduce it to a single dimension because it's going to give you 2-dimensional after you finish training, or 3 dimensions actually, because your input is 3 dimensions, right? So your output will also be 3 dimensions, but you squeeze it into a single dimension that contains this 9. This 9 is still again the 9 elements in the sequence, right? The 9 positions in the board. And what we are saying is the logits it should give you is a kind of probability distribution of which of these positions should be the right move to make, right? Then there's something we call masking of illegal moves because you don't want remember you're training a model, a neural network model, so it will still give you some probability distribution for illegal moves. But we don't want to consider those because you don't want your model to make illegal moves. So we mask the illegal moves. So what happens then is that you take the full 9 positions, right? So touch.full means you give everything a um, minus infinity value, right? Okay, that's a mask. Then, so that means moves that are illegal will get minus infinity. And then moves that are legal will get the actual value from that logic. So for M in moves, so remember moves come from here, which are the legal moves. So it's only the legal moves that will get their actual values, the actual corresponding values. And these moves gives you the indices, right? So if there are only three legal moves, maybe position 0, position 2, and position 5, moves will be 0, 3, 5. So that means it's only 0, 3, 5 that will have values from the prediction. But the remaining positions on the board that have that are not legal will have minus infinity. So that when you now do this soft max, so remember what we said about soft max. When you do a soft max, right, anything with a minus infinity will become 0. So we'll have a 0 probability and everything else will be boosted. But the total sum of probability in a soft max is always going to be 1. So that's the essence of this soft max. Of course, you take the mass, you divide by temperature. So temperature is like an extra parameter just to bring in a bit of randomness into the thing, right? So if temperature is very high, all of this, everything in the mask will have a very low value. So they'll end up being almost the same, right? But if temperature is low, right, everything here will also be very high. So softmax will kind of make them um, closer to what they will be. So temperature kind of um, minimizes the differences in the logics. Actually, this is what we call okay, we can call it temperature. It's something that is used in gaming a lot. So with that, we now do a multinomial, right? Multinomial is basically taking those ones and the probabilities and picking the one that has the highest probability, okay? And then we pick the one that has the highest probability, and that will be your move. So this is now how you choose a move. So you can see that this choosing move basically runs inference on a trained model, right? And then basically decodes whatever the trained model gives you as numbers into a position. So that's the main thing you see. Also making the move, we started by encoding it, but encoding it is this to tensor input, which is already part of the board structure. So whenever you're using models, right, you need to understand that there are always three steps. The first step is decode, right, the input from the domain specific formats, right? Um, from domain specific formats to a model, readable format. That's a format that you train the model with, right? That's the first step. In any so that's always a step, right? In this case, we use a one hot and the board, this is the main guy that does that. Then the second step, of course, is run, run inference through the model. And then masking illegal moves are additional stuff, right? Okay. So the third thing is then you know, translate, right? Translate the output from the model back to the domain specific format. This is the standard process you always follow when you're using a neural network or any model for that matter in a real world problem. You need to, and when you're training, it is the same process of decoding and encoding. I think we should call this encoding though. It's encoding. So for example, one hot encoding is encoding, right? Embedding is still an encoding thing, right? Then after you do this, you decode. So decode is where you take the output from the model and you translate it back into a domain specific format. In this case, the masking of the legal moves is part of it, right? So it's still part of it because you don't want illegal moves. So this is where it's domain specific because you have to know the game, right? To know what is legal move and what is illegal move. Okay, so that's that. Now choose move with probabilities is just a slightly different implementation where in this case you use a categorical distribution, right? You do the soft marks and then you do a categorical distribution. So in this case, you are not just picking only the move, right? You're also picking the probability distribution of that move, right? The probability of that move, which is kind of to give you a confidence, confidence level for that move. Yeah, so that's the player thing. I'll later on update this player so that if I am playing as a normal human being, then there should be a third player called human player where the move is just to pick something from the keyboard, right? All right, now, so this is kind of the scaffolding around the game, right? The first one is the board, which is a game environment. The second one is the player, which is the scaffolding that allows your model to interact with the game environment. Now we move on to the interesting part where we will now actually do the model that does the game. So we'll start with this. So we are going to do a simple transformer architecture here, right? We will have a positional encoding. So remember, we're using an encoder. We're going to talk about this, but remember when we're talking about the GPT versus, BERT, right? We found that GPTs use, decoder while BERT uses encoder. We'll talk about GANs very soon, generative AI, right? But when we talk about generative AI, you see that those two parts, right, of the transformer model or the general model itself, like that we talked about, you have encoder and decoder, and we found that encoders are good for you know, encoding the meaning in the sequence. You have a sequence and you are able to understand the hidden meaning, the latent meaning, right? That's what encoders do. While the decoders generate output from the latent meaning. So any task that requires generation of output, you would use decoders. But any task that requires understanding of a sequence, you would use encoders. So another simple principle here. We need to understand the sequence. In this case, the sequence is just the 9 positions on the board, right? I want to understand the meaning, which would tell us what the next move should be. So we are going to use an encoder. And if you look at it, the encoder architecture, let's go back and take a quick look. The BERT architecture, right? You have embedding, they have positional encoding, right? This is for BERT, but the generic encoder architecture, which we talked about when we were looking at attention, right? There's input embedding, right? And then there's positional encoding. The input embedding, we have already done it with the one hot, right? So we don't need any elaborate embedding. We already have the embedding. This is where we did the embedding. We already did the embedding here in a way. So it's an embedding for those positions, a simple embedding. So we now need to do positional encoding because remember when you do the embedding, a transformer has no idea of position, right? So for us to bring position into it, we simply just we create an embedding vector here. We basically create an embedding that uses 9 positions, right? 9 positions. While D model is the depth that you want to give to the embedding. So effectively, what this will do is that our 9.3, which is the input, we will convert it to a 9D model, where D model is the depth that we want to give to our transformer attention matrix. So here you can see that essentially you are converting, you have an input that is 9.3. Okay, so you have an input, right? And the input is 9 positions Each position has a depth of 3. The 3-1 hot encoding we did earlier. We now are going to embed this, right? With the embedding. Okay, so we had encoding before. Now we'll have embedding. So let me correct myself. So we will now take this and we'll still have the 9 positions because that's the sequence length. We'll still have the 9 positions. We'll now generate an embedding that is wider. So think of this as kind of feature extraction, right? When we're doing CIFAR, we use 3. Even though we're using CNNs, we went from 3. Some people went from 3 to 32, right? Some went from 3 to 64 and so on. Basically, and then from 32 went to 64, and then from 64 went to 128. So it kind of basically encoding more features in the feature space. So in the same way, that's what we are doing here, right? These 3 now, we are now going to encode into more features here. So it can be 64, it can be whatever, right? But we still have 9 because the sequence length is 9. So that's what this embedding does. Basically, 9 is the sequence length, while D model, which is what you're going to pass in, is this depth, right? Okay. So that's it, right? So the forward is just run it and touch A range 9. So touch A range is going to give you 9 positions starting from 0 to 9, and then you just return the value of X, which in this case, the value of X is going to be whatever you pass in, which is going to be this, right? 9 by 3, or specifically 1 by 9 by 3. That's the input that's coming in, 1 by 9 by 3, where 1 is the batch size. So there's just, or the batch dimension. So there's just a single batch if it is a single position. But if you are training, you can be training on a lot of positions. You can train on, a 1,000 positions. So the batch size here will go to 1,000. If you are using a batch size, like when we are doing data loading and we are loading like, um, 24 as your batch size or 36 or 32, then this will be the number, right? But this number is always variable. And we typically just use the letter B, either capital B or small b, to represent the batch dimension. So this will be 193. And then we will now add position embedding, right? Which will be the number of positions, right? And that will give you this. Okay. So that's how the position encoding happens, right? Even though I am interested in the fact that um, X is a 193, they are not the same dimension. So I wonder how it will handle that. So we'll check we have 9 yeah. Okay, let's continue. So that's the position encoding part of it, right? Remember the position encoding is here. This is where we have position encoding, where we take the encoding for the position and we add to the input embedding, right? So then we now do the transformer, which is the encoder. So with PyTorch, it's really very easy to do it, an encoder. All of the internals have been done for you, so you don't even need to write any code. All you need to do is you do the projection first. Okay, now this makes sense. Um, so we have an input projection. We have a linear. We're going to have a linear projection that will take input of 3, right? And give you an output of D model, which we have already defined as 64. So that is this input projection that is going to give us what I drew before, where this input projection is what will give us that sequence of 9, right? With 3, right? Will now give us a projection of 9 to what? 64, right? Whatever this depth is, 64. So that is what will give us, and that will match the position encoding, because the position encoding is also going to generate a 64 dimension encoding. So that's what position encoding did, right? So yeah, so you have so a position encoding is just an embedding model, right? So an embedding model is reused for position encoding, and then in the forward path that is used to add to whatever comes in. So of course, remember position encoding is always addition. So yeah, so we now have an input projection, which is just a linear model that's going to take the 9 3 and convert it to 9 9 whatever D model is 964 or whatever, right? Then position encoding is also going to create a 964. But those nine are just 0 to 9, basically 9 numbers um embedded. So, and then we have the encoder layer, which is a single transformer layer with the same D model. We specify the number of heads. We are going to have 4 heads here. The feed-forward dimension is D model times 4. Remember, when we said feed forward is this feed-forward network, which is a stack of 2 linear layers, right? And we say that if we have D model coming in here, then this output, this in between output, the hidden output should be X, you know, X, should be DM. Let me put it this way. DM times a certain variable, right? Or a certain constant. This constant in this case is 4. In other words, the output from this first layer will be four times the output here. So if the output is 64, then this will be um, two, 256, right? But this output will go back to being DM. It will be squeezed. So that's why it always has a fan out like that. It goes out and it goes back in. And then this will be a certain multiple of the DM. So that's what is happening here, DM times 4. A little amount of dropper is also included in the entire encoder and then batch first. So this is a single layer of the encoder. So we create the entire encoder by specifying the number of layers of this encoder. And we want to have 2 layers in this case by default. We can increase it. And then we have an output head, which is just a linear layer. And the linear layer goes out to a single logic, right? So again, remember, in order to explain this, the input into the linear layer is D model, right? Which is the size of the embedding dimension, but the output is 1. So remember, the input is coming in as batch, right? And then the sequence length, right? In this case, the sequence length is the number of cells, which is 9. And then the output is this one here, which is 1. So what it means is that we want to be able to predict a single value for each for each cell. So it's going to come out as a probability distribution, right? So that's what that is. So at the end of the day, forward is just stacking all of those together. So we pass X through the input projection. When you pass through the input projection, you now have 9 by D model batch. And then you do the positional encoding, which is also 9 by D model. It's going to broadcast in the batch dimension. So you add the positional encoding. And then you pass that through the encoder and you're still going to get 9 by D model. Then you pass it through the output head, which squeezes it into a single output for each position. So you're going to get batch 9 by 1. And then you do the squeeze to reduce to just 9 numbers, right? That will give you the probability distribution of the output. So that's that. And that's our model for the tic-tac-toe. Now that we have the model, the next thing is we now train. So training is a standard training loop, right? But there will be a little bit of extra stuff. So the first thing is that um, we have what we call self-play. For games, we have self-play, right? Um, you let the game play and then you record its games and you use those games that it's playing to train it. That's basically self-play, right? So, and you can play a lot of different games, right? And you train it based on that. So the training loop incorporates that. So it's not a standard training loop. Let's look at a training loop. So the first part of training loop is that we define a function to play a complete game where we pass in two players, player X and player O, right? So to play a single game, at the end of the day, it's going to return a list of the moves in that game, which is what you will use to train the model some more. So each step is made up of the board position, the current board position, which is stored as a board object, right? The move that was made, which is just a single number, to that's the index, the player that made that move, right? And then the outcome, which is whether the game was a win or a loss. It's as simple as that. So we have a board, a single instance of a board created. It always starts with an empty board. And then we have history, which is going to hold this whole thing, right? Board snapshot, the move, and then the player symbol. So while the board is not terminal, in other words, while the board, there's still moves to make, right? You swap the players, okay? So player is player X. If the current player is X, otherwise player O. So we swap between who is supposed to play. And then once you are swapped, you now ask the player to play. If the player has this choose move with probes, then you call that so that you get the move. You also get the probability, which is the level of confidence in that move. But if not, you just do choose move, right? And then the probe will be none. And then if we are recording the move, we append the move to the history. So you have board cells, right? So remember the board, you make a copy. This is a copy of the board, and you have the cells. Then you have the move that was made. Remember, we have already asked the player to make the move. And the player can be either a random player or it can either be a random player or a neural network player. Okay. And then we have player, which is the current player to specify who is the current player, and then the probability. So that's how we track the history of the moves. And then we track the history, we have not yet made the move on the board. We just ask the player to tell us which move. Right now that we've recorded the history, including the previous position of the board before the move, we now make the move, put the move into the board. Once you put the move in the board is going to change its state to how it is. And we just continue looping like that until we get to the end of the game. And that is terminal. And then after that, we just check out the results to know who won. And if we are saying record, then we can record this entire game in history. So step outcome is the outcome, which we already know. And then we return, the history. So if we want to record, we have to add for step in history, which remember we're already adding history. So for each step in history, we'll now go back and record the outcome. So remember, we didn't know the outcome of the game yet while we were recording this history because the game had not yet ended. We're still playing the game. So this is one of the things that you do when you are when you are doing a game, and you're training a network on a game. You have to, when the game ends, you have to look back through all the moves to store the outcome, right? So that way, this becomes training target data for any model you want to train on this. So with this, you now return history and outcome. But if not, you don't return anything. Um, you only return the outcome. So this is a single game, to play a single game and return data on that game. Then a self-play episode is an episode where the game plays itself, like the AI rather plays itself. So in this case, the model is going to play both sides, right? And will return a list. So you make a player, a model player, and you give it a specific temperature, and then you just play the same game with the player twice, right? You just call play game and record is true. So it's going to record, you get the history and all of that. And then for each step, if the log probability is none, if it doesn't know the log probability, then you skip it. But if not, you calculate the reward, which is outcome time the player that played. So remember, depending on who is playing, the reward can be positive or negative. If I'm the one that played and I won, the reward is positive. But if it is your own turn and I won, the reward for you is negative. So the reward is always negative of the opponent's case. But in this case, the person that we are looking at is the player that won, right? So the player that won will always have a positive reward, right? But the player that lost will always have a negative reward. So that's the essence of this. So outcome is always plus or minus depending on who won. And then player is also plus or minus, plus one or minus one, depending on which player is playing. So by the time you multiply those two, it will give you the reward for that player. So let's look at that. If I am player one, if I'm X, the player number, my player value is one, right? If I won, then the outcome is one. So my reward is one. But if I lost, the outcome is minus one, and my reward is minus one. But if I am player O, that means my player number is minus one. That's the value. If the outcome is one, that means player X won, right? So my reward is one times minus one, which is minus one. That means I lost. But if the outcome is minus one, that means player X lost. So the outcome for me and the reward for me is one, which means I won. So I hope that's not too complicated. So we now append all of this into the list of experiences. This is now what we will use to train the model. And then this log games allows you to log the games. Once you've got a whole bunch of games, then you can run through and log all these games somewhere. Here in this case, we are logging it in a JSON file. I'm not going to go through all the details of this. This is standard code, right? But here, okay, we specify the number of for a specific number of games, right? Okay, in the case of log games, we'll play and log the games. So it's not just logging games that were played before. Um, so you have a player, you play the whole game, you get the history. If the outcome is one, that means X wins. So the stats of X wins is increased by one. If the outcome is minus one, that means O wins. So the stats of O wins is increased by one. But if it's a draw, then the stats of draw is increased by one. And we just keep playing that. And then we for that history, we save it somewhere in the file, right? And then after that, we collect the training history and we still append it to the list. So this does the same thing as the previous self-play episode, except that we are playing two different players and we are logging the games. Right, so that is the environment, that's the game environment. In this case, self-play and all of that. So after all of this, we have done several things, right? The first one is we define the game board, which is part of the game environment. We defined the playing the scaffolding around the player, basically what allows the model to play. Then we define the model itself, which is a neural network model. Then we define a playing the kind of again, the scaffolding around the environment is still part of the environment. The environment is made up of the board and all of this that allows you to play with the board. But all of that does not train the model. At the end of the day, to train the model, we will need to gather the data and use it to train the model. And this is how we do it, right? So we have this function, right, which just checks through all the experiences. Remember, experiences are all the games that have been played, basically. But it includes additional metadata like the probability, like the game outcome, and so on. So we take all of this, right? We use a torch to stack it, torch to basically log the probabilities. So E0, remember in the experiences, E0 is the probabilities, while E1 is the reward. So this is saying when for a particular probability distribution again is the 9 by 1, the outputs from from the prediction that the model predicts, right? So that's experience. Okay. And then so that's the probability. Then the reward is the value, whether it's 1, 0, or -1 for each game. So we basically have those two in two separate arrays, right? Then we can now use mean to calculate the rewards. Basically, this is kind of rewards minus rewards dot mean. So this is kind of a normalization, right? It's kind of a normalization, right? To give you baseline. Then you calculate the loss, which is log probability that times rewards the mean negative log probability, right? So that's what we use for the loss function. You can see that the loss function, we're not using a standard like um, negative log likelihood. In a way, we have to bring in the rewards as well. So we take the probability, we multiply by the reward. So this is kind of the probability is what I said it will be, while the reward is what it actually was. Okay. So we multiply the two, right? And we use that. We use the mean value from that to create the loss function, right? And then we do the rest of normal standard training, zero grad. We do a backward propagation, and then there's a gradient norm clipping. This is to minimize. Yeah, we didn't talk about this, right? Sometimes your gradients can be so high that will lead to vanishing gradients or so. But you find that in situations like this, we use gradient clipping to minimize the gradients. And so you see that what we are doing here is basically trying to minimize, normalize the gradient so to a certain maximum, to a certain average value, basically. We do that before we do the optimizer parameter update, right? And then we return the loss. So this is a single training epoch, right? Um, it's a single training epoch. And then we also have a function here to create the optimizer. So that's kind of how you would train the model, right? So now let's put it all together, right? To put it all together, we have a function that we call a run function. This allows us to run it. We could have run it from the command line, right? But um, I'm going to run it from um, I'm going to run it from let's run it from here. We're going to run it from the um, Jupyter notebook. So yeah, this allows us to run it from a command line, and it has multiple modes. So we have the first mode where you load or create a model. So you create a model, or you can if the model path exists, you load it, right? So this is to allow us to reuse the same model after training it. This is to save the model, to allow us to save the model after training it. And then this is to just run the self-learning. So the self-learning loop is made up of creating the model, right? Creating the optimizer, which in this case, we are just using an Adam with the specified learning rate. Okay. And then we just run multiple iterations. So for each iteration, you switch to a train mode for the model. Um, log games is going to play a bunch of games, right? And then log the game data. Okay. So you pass in the model, you pass in the games that will be played, which is a parameter that you say, okay, number of games per iteration. So in this case, you are playing games, right? And you bring in temperature. Temperature allows the model to make random moves, even when the model has learned. Because one thing is, when you're training a model on games, you don't want to after it has learned and mastered the game or has learned a little bit of the game, it will tend to avoid bad moves. But when a model is avoiding bad moves, especially during training or self-learning, it will never become better because it will never be able to explore some other situations that could lead to better moves, right? So that's where you introduce temperature. Temperature allows you to override what the model has learned. The model will still make random or bad moves once in a while. What it thinks are bad moves once in a while so that it can explore. It's what we call exploration versus exploitation when it comes to reinforcement learning. Unfortunately, we did not do reinforcement learning. But this is kind of a form of reinforcement learning. So in a way, you can say I've touched the subject a little bit. So in this case, Exploration versus exploitation is always having giving the model an option, opportunity to try new moves, even when those moves may be bad, because it will never know those moves are bad if it doesn't try them and fail. So every model needs to be given an opportunity to try new things. If they work out well, it learns from those. If it turns out badly, it also learns from those. So temperature is the parameter that allows to do that. And we saw that what temperature does is basically it overrides what the model has already learned, what it wants to do, and allows it to do more random move selection. So it will select moves. So basically, this is the self-play, right? Generate some games, right? In this case, 50 games by default, right? Collect all the data from those games, the moves that were made, the game outcome, and the policy gradient. So the policy gradient signal here, policy, by the way, whenever you are hearing policy, when it comes to reinforcement learning, especially when you are training models on games and other things like that, policy basically is a distribution of, for each move, each available valid or legal move, what is the confidence level? Let me put it that way. Like, what does the model say, right, should be the correct move? So when you look at that matrix of moves versus the probability predicted, whether, well, it could be predicted or it could be learned or it could be from the training data, right? That distribution is what we call policy, right? Policy is basically which move of all each for each of the moves, what is the likelihood that this is the best move, right? So that's policy. So the gradient of that is the policy gradient. The value, on the other hand, is the outcome of the game for a particular position. So a value of one, for example, will mean I won the game. Value of zero means we drew. A value of -1 will mean I lost, right? So yeah, so we now do this reinforced update, which is what we just described here, where you are essentially training the model. This is reinforced update, where you're now training the model on the outcome of all of the games it has already played, right? So with this one, it will learn which ones were good and which ones were bad, and it continues to improve its own weight, right? So after doing that, it becomes better, right? So in this case, what you are seeing here is that the model is generating its own training data. You can think of it as a form of data augmentation. In normal data augmentation for vision and so on, you do rotation, cropping, and all kinds of things. But in games, right, the data augmentation is for you to let the model play itself and generate more training data that it uses to train itself. By the way, that's how DeepMind trained the world, well, in those days it was a big news that the AlphaGo, became very good in playing Go, a game that computers didn't know how to play before. So that's reinforcement learning. This is actually reinforcement learning in the context of games. Yeah, so this is just printing more stuff. So you have iterations here. You specify the loss, which is the loss function in this case, the number of wins by X, the number of wins by O, and the number of draws. And then the model gets saved, right? So that you will load it again. Then run eval is just another function that we can use to run eval on the model, right? You put the model in eval mode, you put the model into a model player. Think of it like you are, yes, we can use PyTorch for reinforcement learning. A lot of people use PyTorch now. This reinforcement learning is different from, so there are two slightly different meanings of reinforcement learning, right? There's a reinforcement learning when you talk about things like Markov, um, the Markov model and all the rest of them, right? So that's a different thing, kind of, right? It's a different kind of reinforcement learning because that one is reinforcement learning in real time. I like to call it reinforcement learning in real time. When you start talking about things like um, you know, the um, you know, Q learning, reward functions, Markov models and all that kind of stuff, right? That's game theory basically, and that's reinforcement learning. That's learning in real time. As things are changing, the model is learning, right? But this is also reinforcement learning in the sense that the model is learning from its own data, like it's generating. You are not giving it what it should learn from. It is generating data by itself by playing against itself and discovering which moves are good and which moves are not. And you take that data as training data to train the model again. So it's a kind of it's still supervised training, right? But it's reinforcement learning in the sense that the model is reinforcing its own knowledge, right? That's what makes it reinforcement learning. But it's kind of I would call it self-supervised, training because it's still supervised training. You are still giving it training targets and so on. Because that's basically what supervised learning is. You give it input data and then you give it training targets, right? That's supervised learning. Unsupervised learning is you give it input data, you don't give it training targets. So it basically has to figure out stuff on its own. That's where clustering and all other kind. We'll talk about unsupervised training as well when we talk about auto encoders, right? Auto encoder and variational auto encoders, which we'll talk about shortly. But that's for a different kind of thing. So anyway, yeah, you can use any machine learning model, you can use it to do anything. All right, so in this case, we want to run an eval. So we put the model we load the model weights, right? We put the model in eval mode. We stick the model in. Think of this as a car. Think of a model player class as a car. The model is a driver. You stick it inside a car, and it's able to now navigate around the game. And then you create a random player, which is so this eval is like evaluating the model against a random player to see how well it will perform against a random player, right? So at the beginning, the model, when you haven't trained a model, it should probably be even because the model is more or less random as well. In fact, models could even be worse than random, depending when they are not trained at that initial time when you randomize their weights. But after you train the model, right, it gets better. So this is just a var where you are running against a random model. So a random player just picks moves at random. Yeah, so for you to play this, right, you specify the number of games you want to play. So for each game, you now you know, pick who is to play, right? Alternate sides each game. Okay, so this is to switch side each game. So um if for even games, this is even games, right? The model player is the X player and the random player is the O player, right? Model is X is true. This is needed for you to know what to do. But on odd games, the random player is the X player, right? And the model player is the O player, right? And model is X is set to false. So we now run a play game with PXPO. Record is false. We don't want to record it because we're not using this data for training. It's just for a val. And you don't need the experience data here because again, you're not training. So the model outcome, you get the model outcome, right? The model outcome will be outcome, right? If the model is X, because you're trying to know whether model won or lost. So if it's the model that is playing that is X, then model outcome is the outcome. But if not, you give it a minus outcome because it is the opposite, it's the other person's outcome that we are looking at. So with that, we now do the stuff here. If the model outcome is 1, that is the model won, then the wins is +1. But if the model outcome is -1, the model lost, then the losses are +1. Otherwise, it's draws. And use that to do the eval. So this is all the pieces. So now this is the main, right? I'm not going to run this mail again. This was meant to be a command line thing, so I'm just going to skip this, and we're going to run it, here on the board. So far, all we have had here are just functions. We've not done anything yet. So let's go. So we start with we have the board, class, um, we have the random player, we have the model player, and then we have the model, the encoder model, right? The architecture of the model. It's a tic-tac-toe. It's basically a transformer we just go with the defaults here. So 2 layers, two encoder layers, 4 heads in the multi-head attention. The D model, which is the depth of the attention matrix, the depth is 64, right? Which is pretty large and should be enough. Okay. Yeah, so I don't need these imports because I am not running in the context of an app. All of these classes are all available here. So I don't need to do any imports. So yeah, so let's keep going. So play game is a function. These are all functions. We've not done anything yet. So this is where we'll do the training. And again, we don't need all of these imports either. So again, these are functions. So this would typically be the entry game. Now we have different ways to run this. If you run this is a full self-learning loop, right? So if I just do the full self-learning loop, right? Let's see. Um, the full self-learning loop is just run self-learning, right? But if you want to do self-play, you can do model, right? And then this. So, but let's do a few things first, right? I have not saved any model. Um, and I don't even want to. I just want to start with a simple model, an untrained model. So I start with an untrained model and model equals um, um, tic-tac-toe transformer, tic-tac-toe. Let's use this. D model is 64. Well, those are the defaults, but let's be specific. So I haven't trained it yet. Okay. Now, so I have a model that basically is random. It hasn't been trained. I'm now going to run a val. So this run a val will allow me to okay, so run a val is load or create. So I don't need to even create a model. I can just it since there is no stored saved session here, right? There's no saved session, so there is no model. So I'll just run a val without needing to create this. So I'll just run a val. So run a val, we can pass the number of games. Let's go with 100 games, which we have here. By the way, I did not switch on my I don't think I'm still using a CPU, but it's a small model, so I'm not worried about it. So we start with a fresh model. After 100 games, the model wins 38 games and loses 40 games, right? And draws 22 games. Now, it would have been nice for me to see those games specifically. So let's see if we can now. If we can at least print. So here, play game did not, we did not record it, right? So that's why we don't get to see it. But I can always tweak this a little bit just to show the history, right? Um, it probably doesn't give me the history when I'm in eval mode, but I can change this. Um, or I can just print the history. So let's just print the history. History of 100 games. So we can actually look at the games. I would have liked to even print the games. Um, oh yeah, I need to update this. I need to update this. Okay. History was not saved because I did not ask it to okay, I'm going to add a new parameter here just to show the games. It will show the games so we can watch. Let me do that. Okay, so let's look at this. Cells. Um, show game, show board. So I need to have a show board here. Maybe by default it will be false. So we can just print the board. Um, if history, so just the last history. Right. I need to make this function now that will display the board. Uh, so cells move player outcome. Okay, so we can, it's not outcome, it's log probability. Cells move player log probability and outcome. Well, there's no outcome as at this point, but yeah, so we could do um for C, for I C in enumerate cells history. It's best to just do a very simple print straight up print. So we start with this and um okay, cells equals history item cells. So cells 0 um display vals equals um if it is 0, then that is empty. If it is 1, then that is X. And if it is -1, then that is O. Okay. So just something simple like that. Uh, cells, cells 0. So cell 0, cell 1, and 2, and yeah, we'll just continue that way. 0, 1, 2, 3, 3, 6, 4, 7, and 5, 9, 8, 5, 8 rather. Okay, then that's a position. Then we can also print um player. We can also print move, yeah. Then we can also print um a lot of equals time, maybe times 6. Okay. All right. So print equals times 6 as well. Then print empty and print empty, then print equals times maybe 10. All right. So this is just like simple yeah. Okay, so now let's try again and see what I get. Um, run eval. Okay, let's just restart and run everything. So I capture everything. Okay, I need to put in um show games. So okay, play game, show games, show board. Okay, so let's rerun everything again. Okay. So history -1 doesn't exist for the first move. So I needed to make that correction. Okay, so history is empty for some reason. So history is always empty. If record, okay. Hmm. I'm just trying to show us how it looks like when the uh okay, so I think we're getting it now. So let's see. A lot of games played, right? 100 games played. Now, if you look at these games, let me see if I can scroll all the way up. So you see, wow, there are a lot of maybe I don't know if there's a way I can print them all in one line. But you see player zero move is 4, right? Log prop is none. Um, so at this point somebody has won already, right? Because whoever is playing, player O is going to play here and win. And then we start a new game. So in this new game we have X is a position player O is to play. It chooses move 8, which is this one, and it plays. And then player X chooses move 1, which is this, right? So these are just playing random games, right? But somehow somebody should play here to win. But because they're random, they're not really smart. So they're not really smart. So O probably should have blocked here, but it doesn't. It plays here. X now plays here and wins. So anyway, um, just showing you how the games look like. Okay, now so that's just running the evals. So let's not show. Now you train the model. So let's do a bit of training. So we're going to call run self-learning. I'm not going to show all of this, right? We will just do self-learning. Self-learning is going to be self-play and then um, log the games, self-play and log the games. So it basically is going to play against itself with a high temperature, right? That's the yeah. So it's basically going to play against itself. So let's run that. Um, we can use if let's say we do I'll specify the number of iterations, maybe 50 iterations, games per iteration. We can also have 50 games per iteration. And then temperature, we'll use temperature of 1. Temperature of 1 is going to make the model try out a lot of things, even when they are wrong, right? So we record epochs as well. It's also going to be saving it here. So there were 50 iterations. This might take a bit, right? But you can see that initially we have 28 wins, um, 28 wins, X has 28 wins, O has 15 wins and 7 draws. What you find is the draw rate will actually begin to increase. But then since there's a bit of randomness, it's not going to be too high. I'm actually it's funny that I'm getting random draw rate. So model has been saved. If we check here, I think we should see the model. So we have the model in here. So this is the model PyTorch stored here, and then these are the games which we can look at. So you can also see the games as well. Basically, what has been played for each position, right? This is the move player one, choose move three, choose move seven. So this is how the data is now encoded. And then the outcome is one, meaning that player one won, minus one means player one lost, and zero is draws. So this is data that is used to train the model, and the model gets better, right? So these are 40 iterations. You can now see the draw rate is increasing, like I said. The models are really getting good. The number of draws will increase. But here we have a bit more noise. So now after this, I'm going to run evaluation against so yes, so training is complete. So we now have a trained model. I'm going to run evaluation. So evaluation is going to load the trained model, and this time around without showing the board. So it's playing against random, and you can see well, the model is still losing 37 games, but it's winning more. So if we run another round of training, it will probably get better and better. So we can show games equals true. So it's interesting that our model, now if you look at some of the games, let's start from a new game, like here. So it learns a bit more. It actually learns and is playing a bit more strategically, right? So here it's playing this and it's you know planning for win, planning to win, and you can see that O plays O. It doesn't bother to block, and then X wins. So if you train the model a bit more, then you'll be able to get. This is one other thing. If you are training models for games like this, right? You use this kind of eval playing against a random mover as a kind of evaluation. That's how you evaluate a model that you train for a game, right? You won't there's no you're not going to use cross entropy or any of those things. You are going to actually run. If we run self-learning again, I'm going to come back to this. As a matter of fact, right, I'm going to come back and run maybe 100 or 1,000 epochs, right? And we'll now run a val and see how it goes. So I'm going to do this and yeah, so that's it. This is how you can train a model on gaming, right? Something that we don't always do often, but this is a full loop, including um, a uh, self-play loop where it learns from playing against itself and gets better. So next time somebody tells you, "Oh, we did this and we use a self-play loop," yeah, this is to let you know that it's not um, it's not rocket science, right? One thing I did not check here, which I should check, is when we are training, we should switch to we use we use we use a GPU to speed up training. That's in reinforce update. So the model needs to be moved. Um, yeah, so all of this need to be moved. The tensors need to be moved into the CUDA device. So we get faster training. Okay, so that's it. Unfortunately, I think I've taken up the whole time for this. So I was hoping I would still do a little bit of pre-training. Sorry, this is pre-training. So Well, just using a game as an example, but fine tuning. So when we come next Thursday, maybe we'll look at fine tuning. Um, but let me just take a few moments to talk about um, the theory behind generative models, so that when we come back, we will be able to just go into hands-on with generative models. So let's talk about generative models just for a few minutes, maybe next 5, 10 minutes. So what is a generative model? A generative model is basically a model that is that generates. It generates text, it generates images, it generates speech, whatever. It generates stuff. That's what a generative model is. And we're going to look at some of the examples of generative models. So let's just go to it. So when we say generative model, it's a machine learning model that is designed to create new data that is similar to its training data. So effectively, you train it on something, then you ask it to generate, right? This is as opposed to what we have been doing before, where you're asking it to predict or classify. Those ones are called, well, those are, um, we'll talk about them, but they are generally called discriminative models, okay? So when we talk of Gen AI, it's generative artificial intelligence, and that has become kind of like the big thing these days. Okay, but before now, we had artificial intelligence that was more focused on classification, regression, prediction, and so on, right? So in generative AI, the model learns the patterns and distributions of the training data, and then they will apply the same patterns and distributions to generate new content, totally new content in response to new input data, right? So they are learning the underlying distribution, the probabilistic distribution of words, for example, right? The mean and standard deviation of numbers. Those basically they learn things about the underlying data distribution, right, in the data that you're giving it to train. So instead of predicting labels, right, which is what a discriminative model would do, right, you're asking it to learn the probability of y given x. That is what what the classifiers and other predictive models do, right? But in a generative model, you are asking it to learn the probability of the X, the input itself, the probability of the input itself, not the probability of the label given a specific input. That's the difference. Okay, so the applications in today's world for image synthesis, right? For text generation, which is what the LLMs do, right? The autoregressive LLMs and so on. Audio and music generation, you can give it music, you train it on the music, right? It has an internal context or internal hidden, what they call latent knowledge, latent space, right? And then it uses that to generate new music. Data augmentation, where you can generate new data that looks like, previous data. And then representation learning. Representation learning is basically you are training models on data and it learns how to represent that data in a more compact, compressed format. So we'll look at some of it. So when we say discriminative, that's what does classification and regression, right? But when you say generative, that's what generates. So typically, for discriminative, it learns probability of y given x, while for generative, it just learns probability of x, right? So for classification, discriminative is used for classification, while generative is used for data synthesis, whatever the kind of data. Examples of discriminative, logistic regression, linear regression, classifiers, and all of that, sentiment classifier, anything that is classification or prediction, regression is discriminative. While generative, you talk about GANs, variable autoencoders, right? And then diffusion models. We're going to look at some of this. Then for discriminative models, what they are learning is a decision boundary. A decision boundary is basically a line, well, a line in a two-dimensional space, a plane in a three-dimensional space, or a hyperplane in a multi-dimensional space that is used to separate different groups or categories, right? That's what you know a discriminative model is learning. But a generative model is actually learning the full data distribution. In other words, what comes next after this, right? Based on what it has learned. That's what that means when we say full data distribution. So these are examples. In representation learning, which is what you do with the discriminative, you have a data space, right? Then you have an encoder, right? And then the encoder you learns from the data and gives a representation. In other words, it maps data in a data space. It maps knowledge in a data space, which may be sparse and broad and wide, into a smaller representation space, right? Which with things like LSTMs, RNNs and so on, that smaller space is what we call the context, space, the hidden, space, that context vector, right? That's a space where the data is represented. And we represent it with the letter Z, right? While X is the input and F is a function that does this conversion after you have trained the model. Basically, a model becomes a function approximator that is able to, move data from this data space and compress it into representation space. That's representation learning or discriminative learning. But generative modeling is the opposite. You have, information that is compressed in a representation space, and you give it to a generator, and the generator will generate data that kind of matches that representation space, but in the data space, right? That information representation, but in the data space. So you just see this kind of converse, opposite of each other, right? In discriminative space, like I said, it's predicting a probability of y given x. So if x is this, it will predict that y is this. And this is the decision boundary, right, that it is using. And if x is this. So this is an example of image recognition, like the MNIST that we did, right? Optical character recognition. This is mapped into this space, right? So no matter how the zeros or O's look like, it all maps it into y is 0, right? I'm predicting the number 0. And no matter how all the ones look like, it maps it into, oh, this is y equals to 1, right? So it learns a decision boundary. But in a generative model, this 0 is going to generate a number. And this one is going to generate a number. So it's not mapping into a single point in space, right? But into a distribution. And you see that the decision boundary is different here. So the objective when you are training for generative modeling, you have two main approaches, right? The first one is what we call explicit density models, where you are giving it an explicit target, right? So variational autoencoders is an example. Diffusion models, right? They are learning the likelihood directly. In other words, they are learning directly the the um the to generate. Basically, they're learning to generate by comparing what they have generated, what you have given to it, right, as the input. And these are the examples. So you see, you give it an input X, you pass through an encoder. Z is the latent representation. And then you have a decoder that decodes that latent representation back to, a sequence. And that sequence could be the same sequence you want to train it, you want it to learn or train on, or slightly different sequence, right? If it's a sequence model, or even a translation model if it is one language to other, or even image generation where you give it a caption and you give it the image that matches that caption, and it kind of learns how to generate that image. So that's explicit density models. Implicit density models are models where you give it like GAN, a generative adversarial network, which we are going to talk about later, right? So for a GAN, you give it an adversary basically, right? What we call adversarial training. And what you're asking it to do is defeat the adversary, um, deceive the adversary. So for example, you are asking the generator to generate an image that the adversary will not be able to know that it's a fake image or it's a generated image, right? Or generate a string of text that the adversary will not know. So the adversary will always it learns by looking at the score from the adversary rather than looking at the output that it generates. Instead, it's the adversary that looks at the output it generates and comes up with a score. So this is example of it, right? In the GAN, the adversary is called the discriminator, right? And the discriminator is the one that will give a score whether it has been able to detect that what the generator has generated is um, is real or not. So effectively, the discriminator is comparing the actual stuff against what the generator has generated and gives a score. And then the generator is trying to minimize this score, optimize this score, minimize this score by generating something that is more real or as close to real as possible. So these are examples of how they work. So we are going to look at auto encoders today, and then we'll look at GANs when we come back on Thursday. So an autoencoder is basically an artificial neural network that is used to learn efficient encodings, right, for unlabeled data. So an autoencoder is kind of an unsupervised learning model, like we were talking about things like um, you know, using PCA for clustering, right? Using k-means clustering and all of those different methods. Those were in classical methods of machine learning. But in more modern, we have autoencoders. So what's an autoencoder? It basically is a model that combines an encoder and a decoder, right? It learns two functions, right? The first part, the encoder learns a function to transform the input data into the internal representation, right? The latent representation. And then it also learns the decoding function. The decoder learns the decoding function that recreates the input data to match what it was given, but by looking at only the latent representation, right? Not the original data, right? So that's what an autoencoder does. So you can see the schematic of how it works. So you have X, which is an input sequence, right? Or input data. It could be a sequence, it could be an image, it could be any form of data. You have the encoder, which is represented here with F of input, right? And then you have the Z, which is the internal representation. Here is represented with H, right? This is the coded, encoded version of this input, right? And then you have a decoder, which is trained to regenerate this input, right? Based on only the internal, representation that it has learned, right? And then the reconstructed output will be compared back with based on a loss function that compares the difference between the generated X, right, and the original X. And is basically going to use the same back propagation to propagate backwards across the decoder, across the internal representation, across the encoder. So it's a full stack training, right? So you can see that the encoder is F of X, while the decoder is G of Z, where Z is the internal representation. And you can see it's X hat. So we are now training not against Y hat, not against a label data, but against X hat, the original data. So, and that's an autoencoder. And that's why it's called an autoencoder, because it basically learns on its own how to encode, right? By the time you train an autoencoder on the same data that you give it in, it now learns an internal representation that is the most efficient, especially when you give it a lot of data that has a lot of augmentation, has a lot of noise, it has a lot of things. So it actually learns the real essence of that data. So this is kind of a PyTorch implementation. You can see it's very simple. You have an encoder, which is basically a sequence, a linear layer, ReLU, and another linear layer. You have an input dimension, and then you have the latent dimension. So the latent representation will have a dimension. And typically, you see that latent dimension is normally smaller in size than the input dimension. So you do an embedding, right, to input dimension, right? And then you reduce it. So this is kind of what we're even talking about when we're talking about LSTMs, RNNs, and GRUs, right? That they have a latent internal representation, a hidden representation. The only difference is that for those ones, it was a sequence, right? Um, Basically recurrent information. But here it is um it's not recurrent, it's just feed forward. So that's the encoder. Then the decoder will take the same linear layer, right? Latent dimension and expands it out again back into another linear layer with the input dimension, which is the original size, right? And then you pass it through a sigmoid. So this sigmoid helps to kind of calculate um, the probability function, whether it matches the original X data. And that's it, right? That's all. So what the autoencoder is learning is it learns to do a nonlinear dimensionality reduction, essentially dimensionality reduction, just like PCA and K means clustering, right? K means clustering. But the difference is that, of course, you're using a neural network. You can see the input dimension is bigger, the latent dimension is smaller, right? So it learns to do that. It learns feature extraction because the feature extraction, it basically learns to extract the most critical features. Because if you are moving from a dimension of 784 to 32, you are going to end up with the 32 most important features. But unlike previous classical machine learning feature reduction, where what we are doing in that case was we scan through the 784 features and we pick only the ones that matter. No, this one actually generates a new set of features that are a compressed version of the most important features in these 784 dimensions, right? And then it also learns denoising. So if you put in a lot of data, including noisy data, it basically learns what matters and filters out the noise. So that's what they learn. But yeah, the limitation with autoencoder is that the latent space is unstructured, unlike typical ones that we know, and it cannot reliably sample new data. If you give it new data, it's probably going to overfit on old data, and it has a pure reconstruction objective. So this is also another example where you pass an input. The encoder, you can see the encoder is compressing it into a smaller latent space, even though this is using convolutions, right? It's using conv2D. So it's using max pooling like we did to reduce it, right? To this bottleneck, which has a 7 by 7, as opposed to the original 28 by 28. This is for MNIST, right? So it basically 2 by 2 max pooling, 2 by 2 max pooling, but each stage it increases the number of filters. So by this point you have 126 filters, and I think some of you did that with the CIFAR 10 as well as the MNIST. But here you now add a decoder that begins to upsample and expand it again. So we now have it's no more pooling, it's upsampling, right? So it's upsampling from 7 by 7 to 14 by 14, and also reduce the number of features back to getting exactly what we had at the input. And then we see whether it will be able to reconstruct the same input. So those are autoencoders. So like we said, autoencoders have a bit of issues, right? The first issue is that autoencoders are mapping to a single point, right? In the latent space, right? So because of that, it tends to overfit, and it is difficult for you to reliably get new data, right? So what we was the new idea to overcome some of those challenges was what we call variational autoencoders. We are going to look at them in more detail when we come on Thursday. But the variational autoencoders kind of look at differences, right? So instead of mapping the input, right, into a single point in the latent space, right, it rather maps it into a distribution. So the encoder is going to output distribution, you know, into various parts of the latent space, right? So the latent space becomes continuous and smooth, right? Um, and with that, when you now push it back into your decoder, it enables sampling from various points in the latent space, and therefore it gives you more reliable decoding. I'm going to explain that a bit more. There are two main aspects in the variational autoencoders. There's what we call a reconstruction loss, which you will calculate. And then there's what we call a KL divergence. KL means Kullback Libler. Those are the two guys that came up with that algorithm. It's basically an algorithm that allows you to calculate the difference between two probability distributions. Basically, you compare two data distributions and you can calculate the entropy or difference, relative entropy, basically between those two. Right. So it's like thinking about, instead of calculating the difference between two numbers, right? 10 minus 5, that will be single points in space. But let's say you had a distribution where the first distribution had 5, 10, 15, 20, while the second distribution had 2, 3, 8, 5, 16. Now, how do you calculate the difference in those two distributions? That's what the KL divergence allows you to do. So we end up with a loss function that is equal to the reconstruction loss added to the Kullback-Leibler divergence, right? And that is a loss function, the total loss that will be used. So the KL term is used to regularize the latent space and make it not overfit, make it smoother and more continuous, right? So I will talk about this in more detail, but there is something we call a reparameterization trick. So the main issue is that when you are calculating, when you're doing this variational autoencoder, you are sampling randomly in the latent space, right? To be able to do your decoding. Now, because you're sampling randomly from the distribution, probability distribution, that action is not differentiable. Remember, whenever you are doing stuff and you're training, especially with PyTorch and others, you have to always choose differentiable operations so that when you are training the model, you can calculate the gradient. And therefore, when you calculate the gradient, you can calculate the updates and train the model. Any function that is on um, is undifferentiable, you cannot calculate the gradient. And therefore, if you cannot calculate the gradient, you cannot train that model. So that was one of the key challenges with using the um the variational encoders, using the Kullback-Leibler to do the sampling, random sampling, and then using the Kullback-Leibler. So, but they came up with a way to overcome that by rewriting that random sampling in a way that was differentiable. That's what we call reparameterization trick. So what they do is, instead of sampling from the entire distribution, you rather have a kind of base distribution, right? What we call the deterministic part, right? Which is basically a probability distribution around the mean and standard deviations, right? Then what you now do is you now you know sample a a basically think of it like I have a base, and then on top of that base I add extra number. So think about it this way. I need to generate a random number. So I can easily generate a random number between 0 to 1, for example, or between 5 to 10. I can be anything. But that randomness, I cannot differentiate it. So instead of doing that, I now say, okay, instead of generating a random number between 0 to 1, let me generate a random number. Let me have a fixed number, right? Or a fixed distribution of numbers. But in this case, let me make it easy by saying a fixed number, right? 0.5. Then that fixed number, I can differentiate it. Or if it's even from a fixed distribution, like a Gaussian distribution, a normal distribution, I can still differentiate it because a Gaussian distribution has a derivative. So I can still differentiate it. But on top of that distribution, I can now do another random sampling. So I don't need to be able to differentiate that random sampling. We can just call it random noise, right? But it is a random sampling of, maybe you now take random numbers between 0.5 and 1 and add it to the base Gaussian distribution, which is between 0 and 0.5, right? So with that, they were able to come up with a way that, okay, the aspect that is differentiable, which is the fixed part of it, I use that one to calculate my my gradients for back propagation. But the aspect of it that I add on top of the base number, right? Let's say instead of um, trying to guess random numbers um, between 0 to 1, right? Instead, I take numbers from a Gaussian distribution between 0 to 5, right? Then I add any random number between, you know, the 0 to 0.5, right? That's the Gaussian distribution, numbers in that range. Then on top of that, I can now randomly generate numbers again from 0 to 0.5 and add it to the one that is a base number. So that still gives you random numbers, but at least you can then differentiate the part of it that is in the Gaussian distribution and the part of it that is random, that extra term, right? That's what they call the epsilon. So what we now do is that instead of sampling a random range, right, between uh, this directly, right, we sample a random noise variable from a fixed standard normal distribution, right, which is the Gaussian distribution. And then we add that using this transformation. So epsilon is a random aspect. You multiply by the standard deviation and add it to the mean. That gives you the z. But at least the z, the mu is now distribution differentiable because it's the mean. Even the standard deviation is differentiable, right? But this epsilon, right, is the kind of noisy part, and we don't need to differentiate it. We can just allow it to get lost because it is noise. So since mu and sigma are now external to the random sampling of epsilon, they are treated as normal nodes. So they will be calculated, they will be differentiated. Gradients can now flow through the mu and sigma to the encoder, while the epsilon will be lost basically, and you don't need it because think of it as a kind of regularization. So anyway, that's a trick. It's a bit difficult to explain, right? But that's a trick that's used for variational autoencoders to be able to allow them to learn so that you can apply back propagation, apply gradients. And this is just a simple PyTorch implementation of the reparameterization where you now calculate standard deviation and then you now calculate epsilon as a random value in this range of the standard deviation. So you now take that epsilon, you multiply by standard deviation and add it to the mu. So the epsilon is noise. Random like cannot be differentiated, right? But the mu and the standard deviation can be differentiated. So that helps with that. So that's kind of the summary of autoencoders. We'll go into it in detail and we'll continue with the GANs, the generative adversarial networks, as well as the diffusion models when we come on Thursday. And I think that will bring our whole session to an end. So that's it. And thank you very much. I hope we learned something from this. We will also do the fine tuning when we come on Thursday. We'll take maybe an hour or an hour and a half to do fine tuning before we conclude with the generative models. That's it from me.